Thank you very much. Okay. So again, here I should say sorry because the friction force last week. Sorry, I have made mistakes about the things of the friction force. So when you just review, just follow what we have learned today. When to judge the friction force is slipping or no slipping, it's very important. Sorry. And also one more thing is that I think because this uh, chapter is very important in equation of motions and a little bit difficult. So I spent more time than we scheduled for the syllabus. Okay, because I really think it's important. And today we just will finish study about equation of motion, and then tomorrow we will study work and energy, and then the uh, linear moment, angular moment, and linear impulse and angular impulse. Actually, just work and energy plus the equation of motion, you can solve almost all the problems of the kinetics of the rigid body. So that's why I spend so many time this chapter. Okay, and we will finish our study next week. Okay, and then we will have our final exam. This is the 16th week, and the next week will be the 17th week, and we will have our final 18th um, week, just like around, I think, let me check the calendar. So today is 8th, and so we can finish our study next Thursday, and then we can have our final on 23rd or 22. It's up to you. Okay. So anyhow, we will finish our study next week. So let's continue our study. Here, the moment equation about point G, what will be? So the FBD, this is FBD. We know the friction force is to the right, and then we have the AG, MAG, and IG alpha, right? So about point G, we have the normal force. The 30 Newton will have the moment about point G clockwise. If we define its clockwise as positive, so 30 Newton. Here, just like here is the clockwise as negative, so this one is the 30 Newton. And then for the friction force, it will produce also moment about point G, and it will be the force times the moment arm and clockwise, counterclockwise, so it's positive. Here we define positive. And about G, we have IG alpha, right? Because MAG passes through point G, so only IG alpha, because here you define counterclockwise as positive, so should be negative. So A is correct. Okay, A is correct. Here you see, because about G, my center, MAG will have no moment about G. Okay, so the solution answer should be A. A cylinder 100 kg. Yeah, thank you. This is A. A cylinder 100 kg beam is suspended by a cable. The moment equation about point A is, so again, you need to write down and you need to draw FBD. What will be the FBD? The weight and the tension force as FBD, right? And then we can use, maybe this time I use another color. I use green. Okay, so IG, what will be AG? What will be alpha? Here, because it's rotating, right? Standard beam is suspended, and if it's rotating, it will rotating about this, and so it will have AGN and AG tau, right? AGN, AG tau, tangential, right? Tangential acceleration, and IG alpha. So if we calculate the moment about G, what will be? So moment upon point G from the FBD, the tension and the weight produce no moment about G, right? Because they all passing through point G. So how about point A? Passing point A, also the passing point A, right? So from FBD, no moment about point A. Right? So answer should be D. Again, from the FBD, because the tension force passing through point A and the weight passing through the point A, so they will produce no moment about point A, so should be 0 equal to AGN produce no moment upon point A, AG tau produce moment upon the A, and IG alpha, that be IO alpha. So that means IA alpha. That means at this time, alpha equal to 0, right? So the answer should be D. Select the equation that best represents no slip assumption. No slip assumption. We mean for the disk, volume disk, no slipping. The best no slip assumption should be C, right? Because this one we don't know whether it reaches the maximum static friction force or not. This one only works for the disk is moving, so that means volume is sleeping. So here, when it's non-sleeping, so the contact point will be at the IC. We have VG equal to R omega. So we have AG equal to R alpha. So answer should be C. So yeah, thank you. A 50-pound wheel has a radius of gyration kg is given. So the radius of gyration is given. That means the mass moment inertia about g is given, right? We need to find the acceleration of the mass center if m, we have the moment is applied. Mu s equal to 0.3, mu k equal to 0.25. Here, you see the friction coefficient. We have the static friction coefficient. Also, we have the kinetic friction coefficient because we don't know the wheel is sleeping or non-sleeping. If non-sleeping, so the friction force should be smaller than mu s n, right? We need to check that. So for this problem, you can make assumption, and then you need to check out the assumption. You need to verify. Okay, validate. Sorry, you need to validate your assumption. So again, for this problem, we just need to draw its FBD and the KD. The FBD is very simple, right? Here, the FBD, we have the weight, we have the force, friction force, we have the normal, we have the KD, What will be the KD? We have MAG, we have IG alpha, right? Oh, sorry. Here, FA, we just YFA to the right, YFA to the right. Just now, I just write down FA to the left. YFA should be to the right. Again, because if without friction force, okay, sorry, without friction force under the action of the moment, the disk rolling clockwise, right? Clockwise, so the point A has a tendency to move to the left, okay? So that's why FA should be point to the right, just at the previous slides, okay? This is FBD, this is KD, right? And we have four unknowns, the supporting force, normal supporting force, friction force, and AG, the acceleration of the mass center, and alpha, the angular acceleration. Again, we have three equations of motion. The x component of all the forces, sigma FA equal to MAG, okay? Sigma Fy equal to MAGY. So we have the normal force minus the weight equal to 0. And we have for the moment equation, we choose the mass center, so sigma mg equal to ig alpha. Here, because normal force and weight passing through the mass center, so only the friction force and the moment, never forget the moment, okay, the moment. Okay, we have the moment, we have the friction force produce moment about the mass center. So here you define clockwise as a positive. So for the friction force, it will produce counterclockwise moment about mass center. That's why here we have minus, okay? And for the KD, only the collective moment about G, so that's Ig alpha. And here we have four unknown, we have Fa, we have Ag, we have Na, we have alpha. Sure, Na can be calculated directly, but anyhow, Fa, Ag, alpha are not given, and so we need to find out these three variables. We need to provide one more equation. So here we can assume that it's no slipping. So if it's no slipping, just as we said, we will have Ag equal to R alpha, right? This one we have done it. So we can find out the alpha and Ag. And this one we need to check out. It's very, very important that you need to check out the no slip assumption is correct or not. And if there is no slip, that means the friction force should be less than the maximum static friction force. That means the disc is not slipping, right? So it should be the static force, static friction force. However, here the friction force as we calculated is 21.3 bond, is actually is larger than the maximum friction force. So the disc, unfortunately, the disc is slipping. So we do this, okay. Since it's slipping, and this time, no matter it's slipping or non-slipping, the three equations of motions are the same, but the supplementary equation or the fourth equation will be different this time because the disk is slipping. So we can use the relationship between the friction force and normal force Fa equal to the collective friction coefficient times the normal force. And then you see we can calculate the friction force directly, and we can solve uh, Ag and alpha. Here, Ag and alpha. You can check this sum Ag is not equal to R alpha. Okay, so for this problem, we need to know that for the disk is rolling, you need to be very careful whether it's sleeping or non-sleeping. You can make assumptions, but you need to check out whether your assumption is correct or not. Okay, it's very important. Okay, so after all, we have finished a study of equation of motion. We just know that it's very, very important to draw FBD and KD. KD not only include the kinetic force, also include the kinetic moment. And then we got them as two equivalent force systems, so they should have the same result force and they have the same moment about any point. Okay, so that's the key point of this chapter. Okay, so we will continue our study about work and energy. Yeah, work and energy is very powerful, right? We know that. So let's start work and energy. Sorry, I need to share the screen to you. The work and the energy just before the work of the torque developed by the driving gears on the two motors, and we need to find out the kinetic energy. Sometimes we need to find out the work, and then how to calculate the work and the kinetic energy for rigid bodies. First, the kinetic energy of a rigid body can be expressed as the sum of its translational, and rotational kinetic energies. And in equation for a rigid body is in general plane motion, its kinetic energy is equal to translate with its mass center that's mvg square plus rotating about the mass center. Okay, so we have the derivation, and if you are interested in this derivation, you can just look into this and follow the procedures. Okay, but here I just skip this. Okay, because as we said, when rigid body is translating, it can be regarded as a particle. For a particle, it's uh, kinetic energy. We know that is 1/2 times mass times v squared. So for a general motion, we know general motion can be regarded as a combination of translating plus rotation, right? Translation plus rotation. So for translation, and it will be the same with particle, right? And then, as we said again and again, when you calculate the kinetic energy or other terms, okay, just always memorize, just like here, this is kinetic energy for a particle. For which body is translating. Mass is the inertia to resist the uh, the change of velocity, and so accordingly, here should be the maximum inertia to resist the change in angular velocity. So instead of the velocity, we should have the angular velocity for rotation, right? So here, because General motion is translation plus rotation. So we need to have two parts. Okay, so this one just memorize and you have the rules to how to memorize. So this is the formula for any rigid body which is doing general motion. And we know that translation and rotation, they are just specific cases. So if rigid body is just only translating, and translation may be curvilinear or rectilinear, right? So when it's translating, there will be no rotational kinetic energy, or when it's translating, it can be regarded as a particle. The kinetic energy just can be calculated exactly like it is a particle. So it's the kinetic energy is equal to 0.5 times the mass times the velocity square. Here we use the mass center, the velocity of the mass center. However, for a rigid body which is translating, the velocity, the displacement, the acceleration of any point should be equal with each other, right? And if it's rotation, just as we can write down the rotation, they will have translating with the mass center plus rotating with the mass center, rotating about the mass center. And actually, this one, we know that just like here, we know that for rotating rigid body, its velocity of the mass center will equal to Rg times omega, right? Because for a rotating rigid body, any point have a curvilinear path, so the velocity will equal to the radius times the angular velocity. Oh, so we can just replace the Vg with the equation. So we have 0.5 m Rg omega square plus 0.5 Ig omega square. What we will have? We will have 0.5 m Rg square plus Ig omega square. So what is Ig plus mRg square? The mass moment inertia plus the mass times the distance from the mass center to the rotating center. Oh, parallel axis theorem, right? Parallel axis theorem. So this one actually equal to IO equal to mass moment inertia about 0.0. So for pure rotation, generally we just write down the kinetic energy of the rotation, use this one. Okay, it's 0.5 IO omega square. IO is the mass moment inertia about the rotation center. Okay. For general motion, so just like this. Translation with the mass center plus rotation with the mass center. Okay. They have two parts. Okay. If a rigid body rotates about its center of gravity, its translational kinetic energy is at all times. If a rigid body rotates about its center of gravity, or just like my center, okay, center of gravity, its translational kinetic energy will be 1/2 m times Vg squared. So because rotating about the center of gravity, so Vg will equal to what? The center of gravity is fixed. That means the velocity of the center of gravity should equal to 0. So the translation kinetic energy should be always equal to 0, right? The answer should be B, okay? So maybe it's a little bit fast, okay? again, let's review. Okay, the kinetic energy for a rigid body, if it's translating, it can be regarded as a particle. It will be even. It will be equal to 1/2 times mass times velocity square. And actually, any rigid body, its kinetic energy can be regarded as two parts: translational kinetic energy plus rotational kinetic energy. Translational kinetic energy is equal to 1/2 times mass times Vg square. Rotational kinetic energy equal to 1/2 times Ig omega square. And that's why here, when if a rigid body rotates about its center of gravity, that means the center of gravity is fixed. So that means the velocity of the center of gravity is equal to zero. So the translational kinetic energy should be zero. Okay. As it is shown that rod with length of L is fixed to a ball with radius R, their mass both equal to m. If the system rotates about point O, rotate about point O with the angular velocity omega, and the mass moment of inertia of the ball about its centroid is given, please find the kinetic energy of the system. You can choose which one. Can you try to calculate this? And try to calculate this. It's rotation. It's rotating, so the kinetic energy T equal to 1/2 times I-O omega square, right? So here, the point is to find the mass moment inertia about point O. The mass inertia about point O is equal to the rod plus the ball, right? For the rod, we know it should be right. This one, 1/3 ml square. We know about the rod, right? And then for the ball, we know the maximum inertia about its centroid. And then use the maximum, use the parallel axis theorem, right? It will be mass times L plus R squared, right? Here, again, let me repeat. The kinetic energy of the rotating body is equal to 1/2 mass moment inertia about the rotation center times omega squared. So here the point is to calculate the mass moment inertia about point O. How to calculate the mass moment inertia about point O? The mass moment inertia about point O is equal to the what? This one, right? Plus the mass moment inertia about of the ball, right? So for the mass moment inertia about the water is easy. It's 1/3, right? But how to calculate? How to calculate the mass moment inertia about point O of the ball? We only know its mass moment inertia of the ball about its centroid. However, according to the parallel axis theorem, the IOB, we mean the mass moment inertia of the ball about point O, is equal to the mass moment inertia about its centroid plus m plus the distance between the mass moment in mass center to the point O. That will be L plus R squared, right? And then you can calculate. The answer should be this one. Okay. You can check out. Okay. So here you see the point, the key point is to calculate the mass moment inertia. The word length is L and the disk radius is R. The mass amount and disk both are M. The disk rolls on the ground with no slipping. It already gave no slipping. If the velocity of the disk centrally is U is given, please find the kinetic energy of the system. We know that kinetic energy will equal to the kinetic energy of the rod plus the kinetic energy of the disk. So to find out the kinetic energy, we need to decide the motion of the disk. So for the rod, for the disk, we know it's low slipping. So this will be IC, right? This will be the IC. So U and for B, the velocity should point to the right because the velocity should always be perpendicular to the radius, right? And its magnitude is proportional to its radius, right? So this one will be the magnitude, the magnitude should equal to 2u, right? And we know the disk is general plane motion. So for the disk, its kinetic energy should be 2 part, right? Now my center here is C, right? The disk, the IC about disk is given is, okay. So here, omega VC is equal to U. So how about omega? Omega should be U divided by R, right? Because the contact point is IC. Contact point is IC. So we can have the relation U, we mean the velocity of the mass center is equal to the radius times the angular velocity. So substitute that replace omega and replace IC with its mass moment inertia. This one we will find out. Okay, you can check this. Okay, for the disk, you calculate. For the disk, you calculate the mass moment inertia. Okay, it's 1/2 mr squared, and then you calculate the kinetic energy. It will be 2 parts. Move the translational kinetic energy, the rotational kinetic energy. Okay, so for the disk, because it's for the disk, it's general plane motion. So the kinetic energy have 2 parts: translational, rotational. How about the rod? The rod we need to decide. So this is baby, right? And because for the contact point only can be to the right. So according to what we have learned before, we can decide the IC for the rod. So they are parallel to each other. That means the IC will be in the infinity, right? What does it mean? That means at this moment, AB, this is A. AB is actually doing translation. We mean at this moment, okay, it's called instantaneous translation. So AB, the kinetic energy quite be simple. TAB equal to 1/2 V C squared times M, and VC equal to VB, right? Because it's here it's instantaneous translation. So the velocity of any point should be equal to each other. That's why VC equal to VB. VC equal to VB. The maybe I don't use C, I use C prime. The mass center of AB, okay, of the rod is equal to the velocity of the pin B and equal to 2U. So the answer should be which one? Can you choose? Can you calculate? Can you calculate this and tell me? Oh, sorry, I forgot to record this part. Okay. Can you calculate this? So I will give you 5 minutes and then we get back. Okay, 5 minutes. 5 minutes and then I will ask somebody to tell me your choice. Okay. You need to do this by yourself. You need to understand, you need to calculate the kinetic energy, translational kinetic energy, rotational kinetic energy. Translational kinetic energy for any rigid body in zero relation, translational kinetic energy, rotational kinetic energy. For its pure translation, this one will equal to 0. For rotation, we will have pure rotation, we'll have O is a rotation center. And if for general motion, we can use it will equal to the translational kinetic energy plus rotational kinetic energy. So you need to practice by yourself. So practice, and then 5 minutes later, I will ask somebody to tell me your choice. Okay, I will ask somebody to help me to find out the answer. How about the last 3 digits should be 113. Naim? Naim, are you there? The last digit should be 113. Are you there? If you don't respond, if you don't reply to me, I will regard you as absent. Okay. I will tell TA that you actually, even you are online, but actually you are absent from the class. Last 3 digits should be 113. Naim, Are you there? Okay, so another guy. So next digit is 126. 126. Nobody? 126? 128? 128? Are you there? Nobody? So last digit is 211. Wishama. Last digit is 211. Nobody there. 211 and 212. Last digit is 212. Are you there? 212. Thank you very much. Okay. Can you tell me your choice? Or if you have any question about the kinetic energy, because it's a little bit too fast. I know because it's not face to face. So I just talk. I just talk. I just don't leave time for you to think about it. Do you know how to calculate the kinetic energy? Do you know how to calculate the kinetic energy here? Can you tell me? I'm sorry, are you there?
Yes, 老师。
Yeah, thank you very much. So tell me, do you know how to calculate the kinetic energy?
Actually, I couldn't calculate it, 老师。
Oh, do I need to repeat? Do I need to repeat this problem?
Yes,
Do I need
please.
to? Okay. So the kinetic energy we know for a particle, right? For a particle, the kinetic energy, we know that, right? For a particle, the kinetic energy is equal to 1/2 times m times v squared. This is for a particle, right? However, for a rigid body, the kinetic energy will be two parts. Translational kinetic energy is very important. Here should be the velocity of the mass center plus the rotational kinetic energy. Just like the here, I think we start from scratch. Okay, here in the slide, we use G to indicate the mass center. We have the derivation here, but I skip the derivation. I just give you the result directly because we know that just like before, when you have M, V, and this, we will have B, the mass moment inertia, and this will be the angular velocity, just like we have F equal to ma, and F is to measure the motion of the translation, and then we have the moment, the measure the motion in the rotation, right? And the effect of the rotation, so we have the m equal to mass times should be replaced by the mass moment inertia, because mass is the inertia to resist the change in velocity. Mass moment inertia is to measure the change in the angular velocity. And so here is acceleration, and here is angular acceleration, right? And because when we talk about the moment, we need to specify the moment center. And also for when we talk about the mass moment inertia, we also need to talk about the center. So anyhow, we can just use the correspondence to write down the moment equation directly, right? We just replace every variables related to translation to variables related to the rotation. So similarly, here for kinetic energy, we just write down the kinetic energy for a rigid body doing general plane motion, just like here. And then we just have simplifications. If it's a pure translation, so accordingly, the angular acceleration equal to 0. So the kinetic energy for a rigid body translating will be only translational kinetic energy. Okay, this one is easy to follow, right? Also, we know that actually maybe you can write down, you can memorize like this way. The kinetic energy of the rigid body is equal to the kinetic energy of each particle, right? And so it will equal to sigma mi vi square. Okay, and for a translation, we know that for a translating rigid body, the velocity of any point is equal to each other. Vi is equal to v. So accordingly, vi will be constant equal to sigma mi, and sigma mi equal to m. So, right. Yeah, we can do the calculation, we can do the derivation easily here. For a pure translation, no matter it's a linear translation or collinear translation, the kinetic energy of the rigid body can be calculated just like a particle equal to 1/2 times the mass times the velocity square. Sure, the velocity can be the wider as the velocity of the mass center because it doesn't matter for a translating rigid body, the velocity of any point is equal to each other, right? This is for pure translation. For pure rotation, we can write down as translation kinetic energy and rotational kinetic energy. And because we know that Vg is equal to R omega, so we replace the Vg to this equation. We will have T equal to 0.5 m r omega squared plus 0.5 the rotational kinetic energy. Similarly, we have omega squared, m r squared plus ig, right? And mr squared plus ig, according to the parallel axis theorem, this is actually the mass moment inertia, right, about the rotation center. That's why for pure rotation, the kinetic energy will be equal to 0.5 I omega squared. Actually, maybe we just can derive this way. The kinetic energy of the pure rotation is equal to the sum of the kinetic energy of each particle. And according to the rotation, according to what we have learned about the kinematics, for any particle, the velocity vi is equal to ri times omega, right? So equal to sigma 1/2 mi ri omega, right, square will equal to sigma mi ri square times omega square. Omega square will be a constant, will be out of the summation, will be mi ri square. How about this one? This one is actually the definition of the mass moment inertia about point O. This one is actually the definition of the mass moment about point O, mass moment inertia point O. So we can verify that for pure rotation, the kinetic energy of the rigid body which is rotating, its kinetic energy is equal to 1/2 times IO. IO is the mass moment inertia about the rotating center times the angular velocity square. Okay. And so for a general plane motion, we know that the rigid body for is subject to general plane motion can be regarded as a combination of translation plus rotation. Here, the base point is very, very specific. We choose the mass center. We don't derive this, okay? We don't just give the strict mathematics verification. Just memorize it, okay? Translational plus rotational. This is easy to understand, but every time you should be careful. We only talk about the mass center, okay? That's like the equations of motions, okay? We just have the kd to locate at the simplify to the mass center, okay? So here again, the mass center. And so for general promotion, it will the kinetic energy will be translational kinetic energy that will be 0.5 times mass times Vg square. Vg is the velocity of the mass center plus the rotation about the mass center. That will be the 0.5 Ig omega square. Okay. This is the definition of the kinetic energy of a rigid body, which is doing plane motion. Okay, so that's why here when we say if a rigid body rotates about its center of gravity, that means for this rigid body, its center of gravity is fixed. So its velocity, then we mean the velocity of the center of gravity is equal to 0. So accordingly, the translational kinetic energy 1/2 mvg squared will equal to 0. That's why here we choose answer B. The translational kinetic energy should be 0 at any times because it's fixed, got 0 velocity. And then we give another example, just like here, we need to calculate the kinetic energy of this rotating system. For this one, we have already calculated the mass moment inertia about point O right before. But here, we need to calculate the kinetic energy. So we know its rotation. So it will, the kinetic energy will equal to 1/2 times IO, mass moment inertia about point O times angular velocity squared. So here we want to find out the kinetic energy, but actually we only need to find out the mass moment inertia about point O. So to find about the mass moment inertia about point O, we need to calculate the mass moment inertia about the watch, right, and about the ball, right. For the watch of the mass moment inertia about the point O is easy. We have calculated this before, right? But however, for the ball, we need to use the parallel axis theorem. It will be equal to the mass moment inertia about point O will equal to the mass moment inertia about its mass center plus m plus the distance of the o-axis and to the mass center. That will be L plus R squared, right? And then you calculate the mass moment inertia about the system and we place them and you'll find out the answer should be C, okay? And then we just give more example here to calculate the kinetic energy of the system. We calculate the kinetic energy of each rigid body and then add them because kinetic energy is a scalar. Okay, so the system, the kinetic energy of the system is actually the sum of the kinetic energy of each rigid body. So here we need to calculate the kinetic energy. This is the A point. Okay, we need to calculate the kinetic energy of AB and the disk, right? To calculate the kinetic energy of the rigid body, we need to judge its motion, whether it's translation or rotation or general plane motion. And definitely for the disk, it's general plane motion because we know the disk is rotating without no slipping. So this is a contact point. And for the disk, its kinetic energy should have two parts, translational, here is C, okay, and rotational. So VC is given. We need to find out IC is also given because we know it's a disk. And we need to find out omega. We need to find the angular velocity of the disk. After you find out the angular velocity with the should be equal to u divided by r, you need to know y is equal to u by r because this is the IC. And so u will equal to r omega, right? Will equal to r I u will equal to r omega. So you can find omega and you can find the kinetic energy of the disk. And then except the kinetic energy of the disk, we also need to find the kinetic energy of the rod. Again, you need to decide the motion of this rod is actually how to decide its motion. We know for the pin B is not only can be decided by the motion of the rod, also can be decided by the motion of the disk because this is IC. And so for pin B, because it's the top, okay, pin B and the velocity should be 2u, right? Because the velocity of the disk should be proportional to its radius to the IC at this time, right? So the velocity of pin B is to the right, and because we know that for point A, the velocity also is to the right. They are parallel to each other. VA is parallel to VB. So according to what we have learned before, for AB, the IC actually should be located at the infinite, or the IC or the angular velocity of AB at this instant is equal to 0. That means for AB, we only got translational kinetic energy. TAB, you only got translational kinetic energy. And then TAB plus T disk, the system would be TAB plus T disk. And you can find out the answer, okay? So you should do this and then find out the solution, okay? Just do it now and then upload your solutions online, okay? You need to do this, okay? You need to figure out. You need to write down your solution, okay? You need to write down the procedures, okay? And then you need to find the kinetic energy of the system of this one, okay? I already tell you how to do this, but you need to do it by yourself. Okay, you need to upload in the WeChat of your solution. See you tomorrow.